Hello. Today I want to talk about floating point again. Now we've been talking about the software side of floating point. By that I mean the definition of how floating point is stored and how you interpret the bit pattern for floating point and that sort of thing. But now let's talk about the hardware that actually performs the floating point. So if we go to our familiar diagram of a computer system, we have a CPU and we have memory, and the CPU is connected to memory by 3 buses. You know, the address bus, the data bus, and the control bus. So now, in order to execute floating point, there are really 3 choices. The first choice is that we don't have any hardware at all. We actually have a library of software routines that run on the CPU, so they use integers, and these software routines can execute or emulate floating point operations. There are several different ways that you can do that, but a floating point value can be represented by the ratio of 2 integers, basically a fraction. And you can store those 2 integers and you can manipulate them in the CPU. So if we have, just go to another page here, if we take x as an integer and y as an integer, we store that integer, we store that integer, and then if we want to multiply that times another, so this represents one floating point value, this represents another floating point value. You know how to multiply, right? So the answer is this. This is the multiplication of 2 integers. Here's the multiplication of 2 integers. The CPU can do that. So we're representing everything in fractional form as the ratio of 2 integers, and only when we actually want to, let's say, transmit the floating point value as a floating point value or display it or something like that, only then do we have to get away from this. And you can convert this into, you know, the decimal equivalent by doing integer division and only keeping the integer part of the division, and then going on to look at the fractional part and doing divisions there, and eventually you build up the characters that represent that floating point value. So that's one way of doing it. In fact, that's how floating point was done at first, because when the floating point format was first proposed, at least in the consumer market, there wasn't any hardware to perform the floating point operations. It was all done in software. Okay, well, now another possibility is we completely redesign the CPU and we include floating point hardware in the CPU. So that means that the CPU basically has to have a floating point ALU. That's certainly very expensive to do. And the third option is the one that manufacturers went with historically. And the third option is that we put, camera seems to be missing the top of that. I even bolted this camera to the tabletop just so I must hit it or something. I don't know what it is. This is called a floating point unit. And basically, this is a CPU. It's got an ALU in it. It's got a register file in it. It's got an instruction register in it. It's got a flag register in it. It's got a lot of things that you would recognize as being part of a CPU. And this floating point unit is specifically designed to do floating point. Well, in order to do floating point, it's got to be able to get values into it. So how do values get into this thing? Well, there's a couple of ways that that could happen. One is this could be mapped into the I/O space of the CPU, and the CPU could do outs to transfer data into this thing. And then it could do ins to get answers back. Yeah, that's certainly possible, but that's not a very efficient way to do it. We want this to be as autonomous as possible. So here's the way it works. First of all, this being a small CPU means that it has an instruction set. There are instructions in binary form that tell it what to do, just like over here. And so the floating point unit is going to watch the data bus. And when an instruction is being fetched, the floating point unit looks at the value being returned by memory to the CPU, which is the instruction in binary form. So that instruction appears right here, and the floating point unit looks at it. And if it's a floating point instruction, then the floating point unit loads that instruction into its instruction register and begins to execute it. Now at the same time, the CPU also loads the floating point instruction into its instruction register. And the CPU looks at it and says, oh, that's a floating point instruction. I don't know how to do those, so I'm not going to mess with it. So in theory, that's the way it works. The floating point unit does what it's supposed to do. You know, it may add 2 items in its register and store the result in a 3rd register. That's entirely possible. However, a lot of time, well, let me go back a second. If this is a Harvard architecture, then what we're talking about, this would be the instruction memory, because the floating point unit is looking for instructions, and that's all that's on the data bus in a Harvard architecture for the instruction memory is instructions. If, on the other hand, this is a Von Neumann architecture, then there's only one memory. That means that the floating point unit, as well as a bunch of other stuff in the computer system, needs to know whether the CPU is doing a read of data or a fetch of instruction. And so in the control bus, there is usually a signal that says this is an instruction fetch that's going on. So, you know, in the control bus now, we've got things like address strobe and data strobe and read-write and I/O mem, and now we're talking about instruction fetch, and there may be something else that I forgot. But anyway, the floating point unit needs to know when there is an instruction on the data bus so that it can examine it. Now, not all of the instructions that the floating point unit is going to perform are completely self-contained. Data has to somehow get into the register file in here, and eventually you would like results to get out of here. Otherwise, they're just trapped and they're of no use to anybody. So the floating point unit has to be able to communicate with the outside world. And usually what it wants to do is you want to perform floating point loads and floating point stores. Just like the CPU can store integers and load integers, the floating point unit needs to be able to store floats and load floats. So part of the instruction set for the floating point unit is a load and store capability. So let's see what happens if, now I'm not positive that this is a correct instruction, but let's just say we have an instruction that's floating point load. Okay. Now actually, at least in the MIPS world, when you do this, there is an additional character which is either an S or a D, or actually there's another one, W for word. This means we're going to do a load of a single precision floating point value. This would mean we're going to do a load of a double precision floating point value. And interestingly enough, this means we're going to do a load of an 80-bit integer. The floating point unit internally holds all values in 80-bit format. Now, this was done in order to ensure that round-off error, when you're doing a lot of floating point operations that are strung together, you take the results of one, like you're adding a big old column of numbers. You're doing your bank account or something. So you've got a long column of floating point numbers, and when you add them up, you know there's going to be round-off error. Well, if we do it in 80-bit and our largest is a 64-bit floating point number, that gives us quite a bit of play before round-off error creeps down into the 64th bit. So it's a way of making sure that long strings of calculations do not produce round-off error. But since we've got these 80-bit registers, somebody decided, hey, why don't we work on 80-bit integers? So they do have an 80-bit integer data type, but we're not going to worry too much about that. We're going to do a floating point transfer. So the CPU has been reading these instructions. Okay, it reads an add I. That's an integer instruction. The CPU can execute that. And then there's a multiply. That's an integer instruction. The CPU can do that. And then there is an fadd. Now that's a floating point instruction, but it's completely self-contained in here. It will have three arguments: where the result goes, where the two operands are. So that all is self-contained. And then, you know, maybe we do another integer instruction. There could be a jump, but eventually we get down here to the floating point load, and we want to load. I should have done this where I had more room here. We're going to do a floating point load, and we're going to put it in floating point register 3, and we want to load from the address okay. So now this is an integer register. That's in here. We're using indexed register addressing, but it's the integer register that's supplying the address. Floating point register is up here. So what we're saying is go out to memory to the location found, or to the location computed by the value in R6 plus 5. So R6 and 5 get added together, shoved out on the address bus, memory responds, sends back whatever is there. Well, it's supposed to go in FR3. The CPU doesn't care about what's coming back. The CPU is not going to latch that data into anything. but this guy will. See, this guy loaded that same instruction at the same time the CPU did. So now both of these are looking at exactly the same instruction. They each know how it works. The CPU is responsible for fetching the data. So the CPU adds R6 and 5, pushes that out onto the address bus, the memory responds, and the floating point unit latches the value into register 3. Okay, if this is a Van Neumann architecture, then there's only one data bus. So the floating point unit can fetch instructions and grab data off of it just like the CPU does. If this is a Harvard architecture, then the floating point unit has to be monitoring the instruction memories data bus to fetch instructions. And then it also has to be attached to the data memories data bus to fetch values. So it gets more complicated in a Harvard architecture because there's basically 2 data ports that the floating point unit has to check. So that's how a value would get in to the floating point unit. Suppose, on the other hand, we had a floating point save. I'm going to use SV for save. And we're going to save basically the same thing. We'll do the same thing here. Now, in this case, we want to take what is currently stored in floating point register 3, and we want to copy that into main memory at the address R6 plus 5. So when this instruction is fetched, again, both units both units get the instruction. The CPU is the one that fetches it, but the floating point unit also grabs it and puts it in its instruction register. And the floating point unit looks at this and says, okay, I'm supposed to take what's in floating point register 3 and send it to memory. But I don't know what the address is because I don't have register 6. So it's up to the integer CPU, again, to form the address. So the integer CPU forms the address and puts it out here. Now, floating point units are pretty slow. Not to mention that if you have a 64-bit floating point value and it's only a 32-bit system, going to have to be 2 transfers made to get that into memory. So the CPU calculates the beginning address of the transfer, and when it spits it out, the floating point unit copies that address into a special address register that it has. At this point, CPU is done. It's calculated the address and it spit it out, and the floating point unit has the address and the CPU is done. Generally, the CPU will just hibernate at this point until the floating point instruction is done. It is technically possible that the CPU could continue to fetch instructions from memory, and as long as they are integer instructions, the CPU could continue to work while the floating point unit is also working. Now, eventually, the floating point unit is going to want the bus to transfer those values, and so it will issue a bus request, which would interrupt the CPU and allow the floating point unit to do it. But that's pretty complicated. I think most CPUs just hibernate till the floating point unit is done. So the CPU calculated the address, put it out on the address bus. The floating point unit copied it. Memory was not told to respond. And so it basically just went up here. So now the floating point unit takes what's in register 3. The floating point unit can drive the address bus using its address register. So it drives the address bus, It tells memory via the control bus that this is a write. Here's the address, it's a write. The floating point unit can put data onto the data bus. Memory is told to latch the data. Then the floating point unit will, if it's a 64-bit transfer, the floating point unit will increment the address value that it has, repeat it with the second half of the 64-bit value that gets sent to memory. And then the CPU can continue on. So this floating point business it's a coordinated effort on the part of the CPU and the floating point unit. The CPU is responsible for fetching the instructions and doing the addressing. The floating point unit is responsible for executing the instruction. Because there's such a close cooperation here, and because the floating point instructions are embedded in the instruction stream for the CPU, these two units are conceptually glued together as a single CPU that has both integer and floating point capability. But they can exist as two entirely separate, physically separate units. Back in the early days, this might have been an 8086, and this was an 8087. The floating point unit was an 8087, and then when they went to the 8286, this was an 8287. Although they made a big mistake in that one. When they make the 8287, they made a mistake on the silicon, and it didn't divide correctly under all circumstances. There's practically an infinite number of division problems that you can come up with using floating point. And it took about 38 minutes for somebody to find this division problem. I don't know how they did it, but it was very embarrassing. And Intel had to go in and completely redesign a portion of this and then regenerate it. And that is very expensive. Redesigning it on paper is not bad, but when you have to make a new mask so you can make new silicon, that is very expensive. So you want to make sure you do it right the first time. It is also possible and common these days for the floating point unit and the CPU to both be on the same piece of silicon. They're still separate modules if you look at it under a microscope, but they are on the same piece of silicon, which means that these buses can be very, very, very fast because they're very short and they are in a very controlled environment on the surface of the silicon. Whereas if this is a separate chip, then these buses are all on the motherboard. And as a result, they're much slower. This is called a coprocessor because its instructions are in the instruction stream. That makes it a coprocessor. That means that this processor knows something about those instructions. This guy doesn't know anything about integer instructions except they're not mine. But the floating point instructions it knows how to execute. And it executes, there's things like add, of course, and subtract, and there's multiply, and there's divide. And then we get into things like, let's say, e to the x, and log of x and sine of x. And so you've got transcendental functions and you've got exponential functions. You've also got some constants built in. Pi is usually built in. E is built in. Although you could certainly get E by executing that instruction where x is 1. There's a whole bunch of instructions that this thing knows how to execute. Um, and don't forget that, you know, these can be done on either single precision or double precision floating point values. Coprocessors are very important. The MIPS processor, which is the sort of what we've been studying in class, the MIPS processor is designed to work with up to 4 coprocessors. One of them is the floating point unit. Now the memory controller in the MIPS system is also a coprocessor. So somewhere out here, there's another coprocessor that is actually handling transfer into and out of memory. When you start getting banked memory like we have now, then you really need a controller, because it's possible to read simultaneously from different banks. Now, obviously, there's only one address bus, but the memory controller can keep track of all of that and produce results faster if the results are from different banks, and the memory controller takes care of all of that. So that's 2 of the coprocessors in a MIPS system. And other coprocessors are either available or envisioned. You could have a graphics coprocessor. You could have a vector coprocessor. There are practically an infinite number of coprocessors that could be imagined. Now, whether they're available or not is completely different. But a coprocessor is an extension to the CPU. And in this case, this extension adds a new data type. That's really what it is. It's adding a new data type. This one knows how to handle signed and unsigned integers. It knows how to handle Booleans. It knows how to handle characters. This one adds a new data type, floating point, and the hardware necessary to handle that new data type. So that's a brief overview of how the hardware works when you want to add floating point to your system. So I hope that helped, and I will see you next time.